Okay, let's begin Pathways 3.58. This is involving the second half of Chapter 3, which starts to talk more about balancing chemical equations and the stoichiometry, or the whole number ratio, that materials combine in when they react. It turns out chemical reactions always proceed by a very specific ratio in which the reactants combine to make products, also with very specific ratios. So practice balancing these equations is useful for us, okay? Problem 3.58 presents 4 different reactions that we're said to balance. The first one in part A involves copper and sulfur. We're going to combine solid copper, solid sulfur to make this product, okay? The copper sulfide, also solid. The terms in parentheses after the reactants and products indicate the phase. They can be solid, liquid. We have some examples of aqueous, and also gases down here at the bottom, okay? So we typically use that to denote the phase of the reactant. So if we're going to balance an equation, we always like to see elements that are by themselves as reactants or products, okay? Because that makes the ratioing of the reactants and products a little bit easier, because if I change this number out in front, which changes the number of copies that are involved in the reaction, it does not affect anything else. And that's kind of golden when you're balancing reactions. So oftentimes, as a strategy, I try to balance things that are standing alone last, okay? Because I can put whatever number I want out in front, and it doesn't change anything else except copper, or except the sulfur. And this one's even better because it's not, and this you've got the 8 down here that you're going to have to contend with. Here it's just a 1, so whatever number I put out in front, that's how many copies I change. And that brings me to an important point, because these numbers that are out in front, if it's not entirely clear why we're putting them there, it corresponds to the number of copies of that particular substance, number of molecules, number of atoms, number of formula units that are combined in the whole number ratio. Now, we can change that all we want, but we cannot change the identity of the substances themselves. In other words, the subscripts here, the H2O, we can't change the substances involved. We just change the number of copies that we use in the reaction to make the mass balance, okay? So that's an important point. Okay, so let's just dive in and practice this. The first reaction, we make Cu2S, okay? This is set. This is what we make. We can't change the identity of the product. All we can do is change the numbers out in front, the so-called stoichiometric coefficients, to make the reaction balance, okay? Now, as I mentioned, as I'm looking at this, I try to leave this one alone because it's a standalone. I can put whatever number I want there later to make it balance. And that's very flexible. So I leave that flexibility to the end, and I turn my attention elsewhere. Now, in this particular example, there's only one other element involved, sulfur. Sulfur appears here, and sulfur appears here. So there needs to be some fixed number ratio between these two to make the mass balance. Okay, now, in this particular case, I use S8 solid. This is how sulfur comes packaged as a solid. I can't change that. Nature has determined that for me, and I'm not allowed to sort of break that. Okay, I just have to deal with it. Now, because of that, I notice that for every one of these S8s, I'm going to need to make, what, 8 copies of my product, because there's only one sulfur atom in every formula unit of this ionic compound. So for one of these, I need 8 of these, okay? All right, so now I'm balanced with respect to sulfur. There's 8 on the left, 8 on the right. What about my copper? Well, by virtue of putting this 8 out in front, I've made 8 copies of this material. Each one has 2 copper atoms. So that means there's a total of 16 copper atoms now involved on the right. But fortunately, I can go back and put a 16 over here and balance that without any trouble whatsoever. Okay, so if I react these in a 16:1 to 8 ratio, I have mass balance this equation. And now you can see why I chose to do this one last, because it's very flexible. I could write whatever number I want there. And since this copper is uncombined, it doesn't affect anything else. All right, so it doesn't make that out of balance, right? So this can be a suitable answer to this particular problem. Let's move on to B, one that's slightly different here, okay? In B, we've got some P4O10 solid. We're going to react with liquid water, and we're going to make some phosphoric acid. H3PO4 liquid. So it's synthesis of phosphoric acid, we might say. Synthesis just means to create, okay? So how are we going to balance this one? All right, so again, when you're presented with an equation that you need to balance, start looking for one, shortcuts, such as this, things that are just kind of standalone, because you can treat those last, that's helpful. And another thing is sort of make a mental list of elements. Now, when I'm making my mental list of elements, the first elements that I want to key in on are those which are not oxygen and hydrogen, other elements. So in this particular example, one that really stands out to me is this phosphorus, okay? On the left, the phosphorus is in the P4O10 compound, but on the right, there's only one place it can go here, and that's in the phosphoric acid. Okay, so we have one source of phosphorus and one sink where it's going to end up. So that basically means to me that there has to be a whole number ratio between these two that work out to balance the mass balance phosphorus. Okay, so I key in on that element and I start thinking about, okay, well, what do I need this whole number ratio to be? Well, for every one molecule of P4O10, it looks like I'm going to need, what, 4 phosphoric acid molecules to be produced. There's 4 phosphoruses here, and if I put the 4 out front here, because this is just one copy and one atom of phosphorus per phosphoric acid unit, I put that 4 out front, now I've got 4 atoms of phosphorus on the right as well. So by putting that 4 there, I brought my phosphorus into mass balance. 4 on the left, 4 on the right. But of course the other elements are not necessarily in mass balance at this time, okay? Still have oxygen and hydrogen to worry about. So let's think about the oxygen. So here, I've got myself 10 copies of oxygen at present, and then I've got an 11th right here on the left, okay? And what do I have on the right? Well, I put this 4 out in front in the last step. So each copy of this, or each molecule of the H3PO4, it looks like has 4 oxygens associated with it. And I've got 4 copies, so that's a total of, what, 16 oxygens on the right. So I'm out of balance with oxygen. I have 10 here and 11th here, but I have 16 over here. And I can't, just create oxygen atoms out of nowhere. So I have to, modify my counting. Now I have 2 choices where I can modify my counting on the left. I need to add some on the left. I could do it here, or I could do it here. If I change the number here, I mess up things with respect to phosphorus. And that's not going to sound like a good idea, because then I'm going to have to come back and start this process over, okay? So instead of doing that, why don't I put a 6 out in front of my water? So now I have 10 plus 6 oxygen atoms on my left-hand side, and that's consistent with what I have on my right, okay? 4 times 4 is 16. So I brought my oxygen into balance by putting the 6 right here. I still have one more element to go though, and I haven't talked about it all yet, and that's hydrogen. This has no hydrogen. Here I've got 12. 6 times 2. And it looks like, boy, I'm pretty lucky. I've also got 12 over on the right. So by virtue of putting the 6 there in that last step, I've also brought my hydrogens into balance as well. And a lot of times you'll see that will just sort of happen when you balance these equations, because you'll get to this magic ratio between the reactants and products that works for that reaction, and then maybe other elements just kind of come along for the ride. But nonetheless, this works for my balanced chemical reaction for the synthesis of phosphoric acid. Moving on to part C. We have this compound B2O3, solid. We're going to react it with sodium. Remember, this is a polyatomic ion, the OH. We call that hydroxide. Hydroxide, OH minus 1. That's sodium hydroxide. That's going to be one of your more important polyatomic ions. It's going to come up a lot when you start talking about pH and aqueous chemistry in water, as it turns out, okay? But it's hydroxide. Now, this particular material is aqueous, AQ. Now, remember what aqueous means? It means that I've taken that ionic compound, that solid, and I've dissolved it up in water. It's dissolved, basically. It would look like a clear, colorless solution of water if I could actually see this. But aqueous means that the ions which are present, the Na+1 cation and the OH minus, are hydrated. They're surrounded by water molecules, okay? So they're floating around in a beaker of water. That's what the aqueous state is. Nonetheless, I'm going to react these two. I'm going to make this and this. How in the world are we going to balance this then, okay? So let's think about that. Now, again, following this kind of generic framework, there's framework that can kind of help you, but there's also a little bit of trial and error. I would key in on this element, my boron. Remember, I'm going hunting for things that are standalone, that are elements by themselves, or elements which are not oxygen and hydrogen. I like to balance those elements first, okay? So I see this boron and I think, I need to probably try to balance that first. There's probably some whole number ratio between reactants and products that have to be true to make that work. Now, where does my boron go as a result of this reaction? It looks like the only possible place it can end up is in this salt, okay? There's 2 over there. There's 1 here. So it looks like I need a 1-to-2 ratio to be valid between those materials to make this reaction mass balance or make it work, okay? So I'm going to start off with that here at the onset of balancing. Now, after I do that, I'll look for other elements to balance. Again, I'm driven generally by this idea to balance other elements besides oxygen and hydrogen. The ones I'll look at next, or the one I'll look at next, I think probably this Na, this sodium. Right? It seems like other than that, we just got oxygen and hydrogen. So let's go look at sodium. Now, where does it come from? Where does it go? Right? Cotton Eye Joe. That's my joke for this. So look, you got sodium here. You got sodium here. How many copies? You got 6 on this side, 1 on that side. So to make this work, I'm going to need to make that a 6. There has to be a 6-to-2 ratio to make the stoichiometry work. Now I consume 6, I get 6 back. Okay? Can't have sodium ions just disappearing or appearing in your beaker. Okay? Alright, so I've made some progress. I've mass balanced the boron. I've now mass balanced the sodium. Let's move to our other elements, the hydrogen and the oxygen. I'll do oxygen first. Okay, take a look at oxygen. Now oxygen is a little bit complicated because we've got oxygen everywhere, right? Here, 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 here. In fact, every single one of our reactants and products contains oxygen. So elements like this in balancing can be a little bit tricky, as it turns out, because if you change one number, you're kind of changing this magic ratio to make the reaction work in all places, okay? But let's just kind of take an inventory, see what we got, and decide what we can do. So on the left, it looks like I've got 3 oxygens here. I've got another 6 right here. So at present, I've got 9 on the left, 9 atoms of oxygen. What about the right? Well, here I've got 3 per formula unit, and I've got 2 formula units. So I've got 6 oxygens here. Right now, I've only got 1 here, additional 1. And if I add the 1 in, that of course makes 7. Right? That would be a little bit short, because I've got 9 on the left, I only have 7 over here, but what if I put a 3 here? In such a case, I'd still have my 6 here. And now I'd add a 3 back in. That would be 9. And both sides of the arrow will be balanced. So it'd be mass balanced for oxygen, we might say. Okay? Now, our last element, hydrogen. No hydrogen here. Looks like I've got 6 copies here. None here. I've also got 6 copies here of hydrogen. So hydrogen's actually balanced. It came along for the ride when we did the oxygen. And again, you usually see that that's the case, okay? Because there's got to be some kind of magic ratio to make the reaction work. And oftentimes when you get at the end of the problem, you start working that ratio out, other elements will just kind of come along for free, okay? And that's another example of that. So, got ourselves a balanced reaction for this part C. Moving on to part D then, which is the last one for problem 358. Here we've got this compound CH3NH2. We would call that methylamine. This is the methyl part, CH3, it's a methyl group, and the NH2 is called an amine. Anytime you see that arrangement, NH2 bonded to something else, it's called an amine in organic chemistry. It turns out that that would be a weak base in aqueous solution. You'll see that discussion when we talk about pH in these general chemistry too. Okay, but it can act as a base in solution. But here we don't have that because we've got gaseous methylamine. We're going to react it with a gaseous oxygen, and we are going to make ourselves some carbon dioxide, some water, and some nitrogen gas. All of these are gases. I forgot to put the state of matter in, but they're all gases. In this case, it's a gas phase reaction. So what are we going to do about this? We follow the same protocol. Notice things that kind of stand alone. I've already noticed this one and this one, and all other elements besides those, okay? So the things that kind of jump out first then, or besides oxygen and hydrogen, the thing that jumps out first is carbon, and then maybe this nitrogen, okay? Because I always like to do the oxygen and then the hydrogen last, okay? So I look at my carbon, and right now it's 1 to 1. Okay, so that's good, it's balanced. So I move on maybe to the next element. I say, okay, nitrogen. Well, here's 1, and here's 2. So I have a little bit of a problem, I guess, in that, well, I think about, well, how can I balance this? This nitrogen gas, it only comes as N2. It comes in packets of 2 atoms bonded together. And I can't change that. That is, again, determined by nature. I can't erase this 2 and make it balanced because it's off limits. I can only ever change the numbers in front. So it looks like maybe what I need to do is perhaps put a 2 over here. Now if I do that, I've got 2 nitrogen atoms there. And if I leave this just a 1, I've got 2 over here as well, and I'm nitrogen balanced. A problem or difficulty with doing that is in doing that I've now messed up my carbon balance. I need to go back and take a look at that. If I put a 2 out in front, now I've got 2 copies of carbon on the left and only 1 on the right. I need to fix that. Well, fortunately, it's early enough in the problem that's pretty easy to do. Because if I put a 2 out in front, I've now got 2 copies of carbon on the right, as I do 2 on the left. I'm carbon balanced, and I also remain nitrogen balanced. That's good, because now I can go on to the other elements, including oxygen and hydrogen, that I always save till the end. So let's take a look at those other elements then, and kind of develop a strategy for what we might want to do to help this work out. Well, the first thing that I notice here, and this kind of goes back to the beginning of the problem again, is this oxygen is an element kind of standing by itself. And whenever I see that in a problem, that's very beneficial for the balancing. Because again, I can put whatever number I want here in that blank to make the reaction work in terms of ratios of reactants and products. And it doesn't affect anything else except that element. Right? If I change this number, all these atoms will change, and the quantity on the left changes. But if I change this one, only the quantity of oxygen changes. And that's kind of a nice thing. So as I'm looking at this particular problem, I might choose to balance the hydrogen first, and then come back and try to adjust the oxygen as necessary to make it work. Okay, so let's take a look at that and see what we need. So I put this 2 out in front. And it looks like every molecule of the methylamine has 5 hydrogens, and I've got 2 copies of it, so it looks like I've got 10 hydrogens there total, because I have 2 copies of this molecule. Each molecule has 5, 3 plus 2. No additional hydrogen there, don't need to worry about it. No hydrogen there, no hydrogen there. In fact, the only place hydrogen can end up is my products. It's right here in water. I'm out of balance, but I can bring it into balance by putting 5 out in front as my stoichiometric coefficient, indicating I have 5 copies of my gas phase water that contains 10 atoms of hydrogen. Easy enough, 10 on the right, 10 on the left, and I'm happy. Only element that remains now is oxygen. And I hope that you can see what I mean about the advantage of doing this last at this point, because no other place does oxygen appear on the left, but it appears in a couple places on the right. Okay? So what we're going to do is we're going to add up how many oxygens are on the right, and then put whatever number we need to right there to make it work. Okay? So since I have 2 copies of CO2, that's 4 oxygens. And I've got 5 copies of water. That's an additional 5, which makes 9 oxygens over on the right side of the arrow. That's a product. So I need to add 9 oxygen atoms to the left. And you say, oh my goodness, how in the world can I do that? How can I add 9 oxygen atoms? Because these come in packets of 2. Nature dictates that. I can't erase that 2 and put a 9 here. That would be off limits. This oxygen as a reactant comes in a packet of 2. That's how it exists. Okay? So what can we do about this? Well, one thing we can do is we can write a fractional value. What if I write 9/2 or 4.5 oxygen molecules there? That would make it work, right? So if I had 9/2 of these, that'd make the mathematics work. And that would be a legitimate equation. We might want to clean it up a little bit such that all of the prefixes, the numbers out in front, the stoichiometric coefficients, all of them were integers or whole numbers. And we can, of course, do that by clearing that fraction. And the way that works is, notice this is 9 over 2. What if we multiply every number out in front by 2? So instead of having 2 here, we double that, make it a 4. Instead of having this ugly 9/2, we multiply 9/2 by 2, which makes that 9. Instead of having this 2 here, we clear that fraction, or clear it by making a 4, multiply by 2. Instead of having a 5, again, multiply by 2, make that a 10. And then lastly, instead of having that be a 1, I multiply by 2 and make a 2. So all I've done is doubled the number of everything, basically, okay? And again, that's okay in a chemical reaction. It doesn't change what's reacting and what's being formed. It's just changing the number of copies that are required and the number of copies that we produce. Perfectly allowed, okay? So this is balancing chemical equations.